Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, we don't have a problem. Today we want to talk about something really cool called impulse. Now you might say, Mr. Bergmann, what's up with the cool helmet? It's the cool aerodynamic helmet for Mr. Bergmann's racing on his bicycle. But we're going to learn about how important a bicycle helmet is and why it works. But it has to do with something called impulse. Now impulse, now you think something's impulsive. They do things quickly without thinking. That's probably a good definition in sort of that word. But in physics, it's related. They do something quickly. It has to do with the force and time. So an impulse, a classic example is a baseball player. When a baseball player hits a ball, the force imparted to the ball happens over just a very short period of time. It's in contact with the ball for just a few milliseconds. We say that the ball has been given an impulse. And it becomes a mathematical equation. Don't panic, it's super easy. I, for impulse, is equal to the force times the change in time. So the force that's applied, let's say the baseball bat, for a short period of time gives you the impulse, which causes the ball to fly into the earth and hopefully hit a home run or whatever it might be. So this is called the impulse, but we're in a chapter on momentum and collisions. Okay, I just talked about a collision, didn't I? When the ball strikes, or the bat strikes the ball. But let's take a look at some of the units on this. So force is a Newton and time is a second. So the unit on impulse, is a Newton times a second. That's pretty simple. But let's break this down just a little bit more. I want you to see a very interesting connection. Force, as you know, is equal to ma. So we could say actually mat, right, for time. A being acceleration. So let's kind of break that down. Mass, but acceleration, as you know, is distance divided by time squared, like meters per second squared, and that's time. Now what could cancel? If we could simplify this a little bit, one of the times cancel, and so that would be m times d over t. Now these are dimensions, mass, distance, and time, but distance divided by time is better known as velocity, or you could say m times v. Now where have we learned this? Well, we just spent a little bit of time talking about this. M times v is momentum, the symbol p. So we can rewrite this equation and we can say I is equal to F delta t, which is also equal to the change in the momentum. By the way, these are vectors, the force and the momentum, because we can play the SOHCAHTOA game, which we will a little bit later. So this gives us some very interesting information about solving problems. And we can even say this, of course, is to m change in velocity, right? Because that's what this equation. So we have a very interesting string of equations that can solve some very interesting problems. And by the way, this is called the impulse momentum. And this will help us solve lots of really cool, awesome problems. In our first problem, we have the guy pushing the cart at 22 kilogram cart. So we're just trying to find the impulse. So impulse is force times change in time. So his force, now we know it's kilograms, so we know, we know it's force. That's 6.5 newtons, and he does this over 1.9 seconds. Now notice in this problem that we don't really care about the kilograms, because that's it. We just multiply these together and we get 12.4 Newton seconds. That's the impulse. All right. Let's look at the second example. This is a bicycle example. A force acts on a bicycle for 12 seconds and we get a change in momentum. So on this particular problem, what have we got going? We've got force delta t, but in this case we're going to set that equal to the change in momentum, and we're going to try and solve for the force, because if you look at the problem again, as you see the problem here, that the time is, so F times 12 seconds, do you see that, is equal to the change in P. Now the P went from 15 to 38, so he went from 15 to 38, that was the momentum. But let's talk about this P, but what is change in P? It's going to be P final minus P initial. So that'll be equals 38 minus 15. We then divide both sides by 12. You subtract that first, and you get an answer of 1.9. Let's talk about the directionality of this, because it says in the problem, as you can see, it says that these are the 38 and the 15 are both in the positive x direction. So what we've got is we've got, our object over here, and it already has 15 momentum. 15, we don't have a particular unit, kilogram, meter per second, and then an impulse of 12 for 12 seconds, and then all of a sudden it gets up to 38. So some kind of impulse got this up, and so it's all moving in the positive x direction, so that's why we get the 1.9 newtons. Let's do one more example, and then we're going to talk back about our helmet. So we got the two friends pushing the car, right? And assuming the car rolls without friction on a smooth surface, the car is at rest initially. The three students give a combined push of 305 newtons. So the push is 305 newtons for a total of 12 seconds. What's the final velocity of the car is basically what it's asking. Well, first of all, let's find what its momentum is. So we're going to use our equation, F delta T equals delta P, and we know the force, that's 305 times 12. And that equals our change in momentum. Multiply that out, I get 3660 Newton seconds. But then if you look at part B, if the mass of the car and the driver is 1360, so the car that we're pushing has a mass of 1,360 kilograms, we can then set this equal to mv, where now m is 1,360. We then do a little math that you can solve for that, and we get a final velocity of 2.7 meters per second. Lastly, let's talk about the bicycle helmet. Why do people wear bicycle helmets? You say it's to protect your head. True. But how does it protect your head? Here's the key. F delta T equals delta P, which is better known as mv. Now, if I'm moving on my bicycle at a particular speed, I can't change my mass, and I can't change my velocity. And if an impulse is put into me by stopping the car, I hit something or whatever, of course, people have died in these kinds of things. So let's think, what's the one thing, I can't change this. All right, and actually, maybe I should make a note here. Force is what kills you. The higher the force, then the more chances of you damaging your body. So the only thing I can actually change is the time of impact. All right, so I can't change my mass, I can't change my velocity. And if you look inside of the bicycle helmet, you'll notice there's cushioning. What's the point of the cushioning? When the bicycle helmet hits the ground, this foam will compress and compress and compress, and it allows more time for the impact to happen. It's going to spread out the force over a greater period of time, hence reducing the amount of force. Again, I can't change these, but if I make this number bigger, right, by creating a device that creates a longer period of time for that force to happen, then I can likely survive the crash. This applies in car crashes. If I'm in a car crash, how do I make this work? If I have an airbag, my body doesn't impact the windshield immediately, a hard surface. It impacts an airbag that takes a long time for it to sort of let itself out. It happens over 4 seconds, 5 seconds versus 0.1 seconds. And then the chance of the force being so great is much, much less. So that's really important when we talk about collisions. If I want to minimize the damage to the individual in the car or whatever it might be on the bicycle, I need to increase the time. So impulse and momentum make a huge difference in the impact, the damage that's going to happen inside of a car. Even crumple zones in cars, what that does is more and more time. We want to have lots and lots of extra time before that impact is felt by the human inside of a vehicle. Anyways, impulse, Houston. We don't got no problems. Bicycle helmets notwithstanding. We'll see you in class.